Assalamu alaikum wa rahmatullahi wa barakatuh. Let me share my screen as usual. All right. So far we have 8 participants out of 13. I hope the remaining guys will join as we move on. If you may recall, in our previous lecture, we tried to perform pipe network analysis. And what is pipe network analysis? Basically, we have a pipe distribution network in which we have total inflow, into the network, which could be from a service reservoir, from water distribution system, and we have the estimated outflows at nodal demands at each node. Okay, this is supplying areas, that is the extraction, the withdrawal from the nodes to residential areas and what have you. Okay, and we want to analyze the flow. So we analyze the flow where we assume the flows in each pipe and we corrected it for every loop. Okay, and at the end we came up with the flows in the pipe, and we came up with the head losses using the Hazen-Williams equation in the pipes, and then we calculated the pressure heads for each node. Of course, we need to know a reference pressure head at the entrance node, which is already given at node A. So we used that, and we kept on subtracting the head losses, okay, up to the last node E, because the pressure head will be decreased only by the head losses, okay, within the pipes. Okay, so we can see we started with 100 and we ended up with 91. Okay, now we will go into the aspect of the pipe network design. Okay, and that's the design of a water distribution system. You see, this is like, if you remember at the beginning, we started with water supply, water development, design capacities for a water development project. Okay, where we look at holistically the overall, components making up a water supply system. Okay, from the intake to the treatment plant, to the distribution system, and then tried to analyze the design capacities. We look at the population forecasting, and the per capita water consumption. That is how to determine the water demand of a community. Okay, that was how we started. And now we are ending with the distribution system. And the distribution system is the last leg, is the last part, because that is, the part that consists of, distributing water to the end users, okay, where individual houses can just, tap from the pipes that are passing, in front of their houses and get water at the appropriate discharge and pressure head. Okay, so now we will give some hints into the what constitute the design of a water distribution system. Of course, part of the design is the analysis which we conducted last week, which is the pipe network analysis. Okay, so we'll be referring to the analysis very often in this case. Okay, so first of all, the system configuration. And the system configuration here, in our analysis, we did not include valves. The system configuration consists of pipes, valves, and hydrants. And these are the basic elements of a distribution system. Hydrants are for firefighting. We all know that. We see them at intervals. Okay, they are used for firefighting and sometimes for sampling, to take samples within the network. And valves are very important because they ensure unidirectional flow. Sometimes at some elevations, either uphill, downhill, you need to install certain types of valves. Okay, so valves are part and parcel of the what we call pipe accessories or appurtenances. Okay, and the pipe system consists of the following. Okay, first we have the primary or arterial lines. Okay, we call them mains. Okay, or main lines, or simply we call them mains, which are pipes, large diameter pipes carrying water from pumping stations to storage tanks. Okay, from pumping station, that is from treatment plant, okay, to storage tanks through the distribution district. These lines are laid in interlocking loops. Okay, they are laid in interlocking loops. They are mains. They have the highest diameter. Okay, usually around 12 inch. Okay, usually around 12 inch. We call them primary lines or main lines or just mains. Okay, and then you have the secondary lines or submains, and they run between primary mains. Okay, and then you have small distribution mains that form a grid over the entire service area. And then you have fire hydrant connections and service connections to individual houses or to individual homes, okay, from the small distribution mains. So you start with mains or main lines, you come to secondary mains or sub mains, and then you go to the distribution mains, small distribution mains, okay, or service lines. Okay, they are also called service lines, and uh, uh, which form the service connections. Okay, service connections to individual houses. And pumping with online storage is a common method. Okay, pumping with online storage is a common method of distribution in which the water is pumped at a fairly uniform rate to a storage tank from which variable demands are met. This I explained. Normally, in this case, pumping with online storage entails that the water is pumped, to a storage tank within the service area. Okay, normally the tanks are overhead tanks so that they are elevated above the ground level to ensure enough pressure head in the pipe network. Okay, so from the probably water distribution network, water will be pumped to the storage tank, which is overhead, and the water will flow by gravity into the distribution network at enough pressure head and flow rate. Okay, to meet the variable demands of the populace. And the other methods of distribution are gravity distribution and pumping without storage. Okay, gravity distribution I explained. When you pump to a storage tank, it flows by gravity. Okay, because once you have overhead tank, okay, if this is the ground surface, you see it will possess potential energy, huge potential energy due to the height. Okay, huge potential energy, and that potential energy will translate into pressure head or piezometric head, because if you remember, the piezometric head, pz, is what? The pressure head plus the elevation head, gamma z. Okay, okay, uh, gamma, okay, wait, yeah, gamma z. So this is the or if we want to make it in form of the piezometric head, we have this is the pressure head plus elevation. Okay, so this is the pressure head and this is the elevation head. Okay, so it is raised above ground level. Okay, the elevation head is more or less, in form of the potential energy possessed by the liquid. Okay, and which will translate into the piezometric head. Okay, which will add to the pressure head of the liquid. This is the pressure head. When it is raised above elevation, above the ground surface, the piezometric head increases. Okay, and that means when the pressure head will rise to somewhere here, okay, depending on losses. Okay, so this flows by gravity into the mains into the distribution network. Okay, it flows by gravity, and then pumping without storage. Sometimes for small towns, the water distribution the treatment plant may just pump directly into the distribution network without storage. In such a case, the supply area will be divided into some zones, different zones. For instance, you pump, let's say this is the area. So you now, let's say, divide it into, let's say, 3 zones: zone 1, zone 2, zone 3. Okay, so today you pump into the water distribution network of zone 1, tomorrow you pump for zone 2, and day after tomorrow you pump into zone 3. The policy here in Saudi Arabia, all houses have, ground storage tank and overhead storage tanks. Okay, the water the treatment plant will pump into the ground storage tank, and then individual houses install pump to pump water to the overhead storage tank. Okay, so this is exactly what happens here in Hafrul. They pump directly without storage. Okay, they pump into the distribution network. So like they pump, they have different zones. Okay, so maybe tomorrow they pump here, day after next tomorrow they pump into zone 2, and day after tomorrow they pump into zone 3. Okay, and then the cycle continues. Because of the storage tank that individual houses have, so probably they may even decide to pump like every other day, to cover all the distribution network. Okay, but more often than not, having a water distribution network with storage tank, cuts a lot of cost. Okay, it cuts a lot of cost, pumping cost, and a lot of other costs. Okay. Now, parts of communities at different elevations are supplied through separate, though interconnected distribution systems, each with its own service storage. Okay, the service storage here, we're referring to the service storage reservoir. Okay, so like here in Afro-Batin, due to the nature of the groundwater surface, due to the nature of the elevation, you have like a valley, some at low elevation, some at high elevation, and all that. So these are like supplied through interconnected distribution systems, each with its own service storage. And hydrants can be spaced 300 feet apart. 300 feet is simply like 90 meters, 90 meters apart. Okay, so they can be spaced 90 meters apart when the fire flow is less than 1,000 gallon per minute, but should be only 200 meter apart for flow exceeding 5,000 gallons per minute. So meaning the higher the flow, the less the spacing, okay, between the hydrants. Okay, when the flow is 1,000, the spacing is 300 feet, which is 90 meters. Okay. Okay. And when the flow is 5,000, the spacing is 200 meters, which is simply 60 meters. Okay. The valves are located not more than 800 feet apart. Okay, the valves are located not more than 800 feet apart in high value districts to allow shutdown of a section for service or repairs. Okay, I told you we put valves at intervals because this will allow shutdown of a particular section to allow for repairs, okay, or some services in case there is leakage in any of the sections, so you can shut down flow to that area and carry out a maintenance work, okay, to fix whatever problem you are facing. Either it's a leakage, you identify the area, replace the pipe, and bring it back in service by opening the valve again. Now for the design flow estimation, now table 1.1, that is, at the beginning I referred you to chapter 1. So table 1.1 indicated that a distribution grid should be designed for a capacity that is greater than any of the two: maximum daily demand plus fire demand, or maximum hourly demand. Okay, whichever one is greater, that is the design flow that we use in the design of a water distribution system. Okay, so we look at maximum daily demand plus fire demand, and then we look at the maximum hourly demand. Whichever one is greater, that will serve as the design flow rate. Okay, and this we discuss and we even solve problems in chapter 1, if you may recall. The demands are based on per passing use and the projected population at the end of the design period, which for the distribution system is the community's full development, since the life of the pipe system may exceed 100 years. This we explain, all the methods for forecasting population. You remember the arithmetic method, the geometric method, the logistic method. So we look at the graphical method, arithmetic, and geometric method, if you remember in chapter 1. Okay, and then the distribution system consists of nodes, okay, corresponding to pipe intersections. Whenever you have pipe intersections, we call it node, and and links representing pipe segments. Okay, we call them links. That is the individual pipe segments. We assume that outflow occurs only at the nodes. Okay, we assume that outflow occurs only at the nodes. That is why in the example, in the pipe network analysis, you have seen the nodal demands at each nodes. Whenever you have more than one pipe meter at a point, then you have like a nodal demand. That is where we assume that the outflows occur. Okay, of course, practically outflows can even occur along the pipe. Okay, but more often than not, for analysis purpose and most of practical considerations, outflows occur at the nodes. The segment-wise flows are estimated based on the industrial, commercial, and residential composition of the area representing the segment and the population density within the segment. I mean, this we already did, how to estimate, the flows. That is the water demand, okay, in particular, because it is based on the industrial need, the commercial need of the area, and the residential composition of the area. Okay, of course, the for urban areas, more water is used than rural areas. And the combined flow pertaining to a segment, and when we say segment here, we mean the pipe. Okay, the combined flow pertaining to a segment is applied at the end node of that segment. Okay, so this I already mentioned. That is outflows do occur at the nodes. Okay, and to optimize design flow, it is important to know the demand patterns of different usages, because the peak demands of those uses may not coincide in time. Okay, so you need to know the demand patterns, because more often that you have like a rush hour early in the morning, everyone trying to bathe, go to work, go to school, and all that. So that is one of the rush hour. And sometimes when we go back from work, from schools, in the evening, also that is another rush hour. Okay, so we need to identify the demand patterns. Okay, in order to ensure that those demands, the peak demands, are satisfied by the design flow. And the network with withdrawals at nodes and the total demand. Okay, so the network with withdrawal at nodes and the total demand as the input is then analyzed by the Hyde-Cross method to determine the distributed flows in the pipe segments and the pressure heads at the nodes. So what are we saying here? Once we analyze the total demand as input, so we now use the Hyde-Cross method to now analyze the pipe segment, I mean the flows in each pipe, as well as the pressure heads at each node. Now, what are the design considerations concerning velocity and pipe sizes? Once discharges in various pipe sections are determined, okay, their sizes are selected by the continuity equation by assuming a velocity of 2 to 5 feet per second. Okay, by assuming a velocity of 2 to 5 feet per second. What is 2 to 5 in meter that's like 0.6 0.6 to 1.5 meter per second. Okay, so so once we know the discharge in each pipe, okay, we can now determine the size. Okay, that's the diameter. Okay, by using the continuity equation. Okay, by assuming a velocity of 2 to 5. Okay, which is 0.6 to 1.5 meter per second, because this is known. Okay, the flow is known, and then we assume a velocity and then determine the diameter, okay, of the pipe. Now, the minimum recommended sizes are for primary or main 12-inch, okay, and then for secondary pipes we use 8-inch, and for small distribution we use 6-inch, okay. In smaller communities, the lines that provide only domestic supplies may be of 4-inch diameter. Okay, so you can see it is decreasing from the mains to the sub-main down to the service line. Okay, so the pipe diameters are decreasing. So we should select our diameter. Our diameter should be within this range, depending on the particular pipe that we are designing for. Is it for the main, for the sub-main, or for the service network? Okay. Now, pressure requirements, which is very important, if not the most important, because uh, although here, like I said, we normally have ground tank, and then which we now use to pump to the overhead tank. But in a case where you don't have ground tank, you know, the water is supposed to rise up to the highest building. Okay, the pressure should be enough so that the water can rise to the tallest building in the area. So what are the pressure requirements? The adequacy of a distribution system is judged from the pressure maintained in the pipeline. So this is very important. And the recommended range for residential areas is 40 to 50 psi, that's pound per square inch. Okay, and it is 60 to 75 for commercial areas. Okay, for commercial areas is a bit higher, 60 to 75, and for residential areas we have 40 to 50 psi. And a minimum desirable pressure in any area, okay, is considered to be 30. This is the minimum, which can supply buildings up to 4 stories. So this 30 psi will be able to supply buildings up to 4 stories. Okay, 4 stories. Okay, of course, it means if you have higher story building, then you will need more pressure head in that area. But the minimum should be 30 psi. And during a serious fire, the pressure in the vicinity may be allowed to drop to about 20 psi. Why will it drop? Because you are using the water. You are using so much water from the pipe. Okay, so that will make the pressure to drop. Okay, and for firefighting purposes, a pressure of 75 psi is desired at the hydrant. Okay, 75 psi at the hydrant and 100 psi within the system. Okay, so within the system it should be 100 psi, and at the hydrant we should have 75 psi. And the normal pressures are, however, increased at such times by turning on special high pressure fire pumps at the pumping station. Okay, you can always increase the pressure by turning the high pressure fire pumps at the pumping station to increase the pressure within the network. And to account for the losses within the system, main lines should be designed for pressures between 40 to 75, because as the water is flowing, you have head losses, which is decreasing the pressure head or the piezometric head within the pipelines. Okay, so the main lines should be designed to have pressures between 40 to 75 psi, and a distribution system should be designed to maintain a reasonably uniform pressure throughout the system, and the minimum for a distribution system should be 30 psi. And the high head losses indicate a deficient system and warrant replacement of existing pipes, because as pipes are being used over time, you know, they tend to have, you know, the inner linings are becoming rougher, and once the inner linings become rougher, then you have high head losses. And when you have high head losses, that means the pressure head will be decreasing. Okay, so high head losses indicate a deficient system and warrant replacement of existing pipes with larger sized pipes where excessive head losses take place. Okay, why do we say larger sized pipes? Because the head loss is lower when you have larger sized pipe. You remember the Darcy-Weisbach equation of head loss of L over D and then V squared over 2G. So when D increases, when D goes up, the head loss decreases. Okay. And when D decreases for smaller diameter pipes, you have higher head losses. Okay. That is because of the frictional effect between, the boundary surfaces and the flowing fluid. Now, a network design project. A first step in distribution design is to sketch a development plan. That is an arrangement of the pipelines that will be needed to serve the area. Okay, meaning you should have what is called a topographic map. Okay, the topo map of an area is simply like, let's say this is Hafrel showing the houses. Okay, showing the individual houses, and everything. So you should have a development plan, and then the extent of detail depends upon the level of analysis. And in the topo map, it shows the elevation. Okay, the elevation, which is the contours. Okay, the elevation, the contours, because you will use the elevation in laying your pipelines. Okay, because more often than not, if you remember, if we are having storage reservoir, uh, overhead storage tank, then it has to flow by gravity. Okay, and we need to identify areas where we have low pressure, high pressure, and all that. So the topographic map, shows the ground elevation, with developments, with the houses, and the extent of detail depends upon the level of analysis and the size of the network. Non-essential lines are always eliminated, and the less important ones are combined using the equivalent pipe method. We explained the equivalent pipe method before. And minor losses are usually disregarded because they can be included via equivalent pipe length whenever necessary. And of course, minor losses compared to the major frictional head losses are very, very small. And in a large system, it may be worthwhile to consider the network comprising main feeders only. For design purposes, we normally design, the main lines, okay, the mains, okay. And it is also is expeditious in analysis of a large system to balance portions successively instead of analyzing the entire system at once. Okay, so you like balance portions, most especially for large system. Okay, meaning you like segregate, you divide it into like different portions and analyze them separately. The centerpiece of the design is a pipe network analysis, similar to that which we did, for the pipe for the using the Cross method. And here you have several commercial computerized programs. I gave you homework. The last homework, you realize, how difficult, how time consuming it is to analyze the pipe network manually when you have just two loops. Imagine a town having, 10 loops, or even 10 or 20. You can imagine, you just cannot do that manually. Okay, you need the help of, computer programs, and there are many computer programs available in the market, like EPANET, designed by the US EPA, United States Environmental Protection Agency, which is free, which is even available online, free. Okay, and you have WaterCard. WaterCard, you may have trial version, okay, but it's not overall free, but maybe trial version is available. Okay, so you have EPANET, you have WaterCard, and you can have many other different pipe network analysis software which are available. And the designs are invariably performed on computer, and the steps of the procedure are explained below with a simple example. Okay, so here we will exemplify, the design of a simple distribution network. Okay, and we use the same pipe network that we analyzed using the Hadicross method previously, in figure 15.14, which represents a simplified network component of a water district, and we want to design the network. So what are the steps? We skeletonized the distribution network of the existing or proposed system. And in this example, the small distribution lines are lying within the figure, which have not been shown. Okay, we just show the main lines. And the project water use patterns for domestic, commercial, and industrial purposes. So we need to project, the water use patterns. That is the water demand, and we project the water use patterns from population forecasting. We first, if the population currently is 2 million, we need to project, let's say in 20 years, how much, how many do we have? Okay, let's say in 20 years, based on the population growth, let's say we have 10 million. Okay, so we now design for this 10 million, okay, based on the per capita water consumption. And that we shall estimate the maximum daily and maximum hourly flows to the end of the design period. I told you what is a design period. That's the period within which the structure is expected to serve its intended purpose. Okay, that is the design period. And we have already shown the different design periods for each of the components of a water supply system in chapter 1, if you may recall. And for hourly flows, use the specific hour in which the summation of domestic, commercial, and industrial demand is greatest. For design, we go for the greatest, so that our system should be able to satisfy the highest demand possible. Because if we design for the lowest demand, it means our system cannot cater even for the average demand or the highest peak demand. Okay, it will fail. So we need to determine the maximum water demand possible, and design our system such that it should be able to cater for the maximum demand at any point in time. And separately, we should estimate the fire flows for the area covered by the network. Okay, and we know how to estimate the fire flow. Okay, from the table, and then disaggregate flows to the various links or segments of the network as indicated. So disaggregate meaning you distribute the flows to the various links and segments. If you remember here, this is the topo map. Okay, let's say this is your pipe distribution network now. Okay, so these are the nodes where we have outflows. So this is the main inflow. So we divide, this area will be tapping from this node, 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 and then this area, the remaining areas will be tapping from this node. So we are disaggregating, dividing the flows. Okay. So here you concentrate the disaggregated flows to the node at the end of the concerned link. These are computed below, okay, and shown in figure 15.14. The fire flow has been applied on the far node E. Okay, the fire flow has been applied on the far node E. I think let me go out of the presentation because I will keep on going back and forth. Keep. All right, so you can see this is the main figure. Okay, the main inflow, and you have the demands, divided. It is the same inflow that is divided, because if you add all the nodal demands at these junctions, they will sum up to give you the net inflow into the system. Okay. happen. Just a minute. Let me. It would be better if I will use. Be looking at it and be explaining. Okay. So we should concentrate the disaggregated flows at the node, okay, and these are divided, okay. If you look at it, okay, if you look at the figure, node B is for link AB, okay. Node B is for link AB, okay. So, all right. So link AB, node B serves link AB, and the flow is 0.35, okay. And C, if you come to C, you can see the flow 0.49, which is divided from the flow, you know, in the 0.21. If you divide 0.21 and 0.28, okay, from link AC and BC, from link AC and BC. What are we doing here? We are dividing the flow rates. Here, the demand 0.35 cubic feet, we are assuming is the flow in this pipe, AB. Now, this 0.49, we are assuming that is the flow from BC and AC, okay? So we have to divide it, 0.49. So here, we are assuming from A and 0.28. So when you add, you have 0.49. Okay, and we move to the next joint, which is D. And for D, we assume the flow rate is entirely coming from link BD, okay, which is 0.42. And then for node E, the final one, so here we add the fire flow here, okay, and we have flow from CE and DE, okay. Don't forget D. DE, here we add the fire flow, okay, and we divide the flow into from CE to be 0.46, and from DE to be 0.42, and then the fire flow to be 2.23, so that at the end the total flow is 4.35, okay. The total flow is 4.35. So this is exactly what I was explaining here. Yeah, you can see this is the disaggregated flows, okay, the nodal demands, okay. So the input at node A, which is giving the total flow, which is 4.35, and when you add the flows for each node, it will give you the same value of 4.37. Now, you now assume a discharge and it's such that at each node, the total flow entering equals the flow coming out because of continuity, isn't it? There is no mass accumulation. So the mass flow rate is the same. Hence, the flow rate is the same. Okay, inflow is equal to outflow. So select the initial pipe size using a flow velocity of 5 feet per second. You remember in the design velocity, it should be 2 to 5, isn't it? 2 to 5 feet per second, which corresponds to 0.6 to 1.5 meter per second. Okay, so here we are selecting velocity to be 5 feet, subject to the minimum size limits. Okay, you remember for main pipe, we mentioned that the minimum size is 12 inch. Okay, for the main pipe. So subject to the minimum size limit, and these are shown in figure 15.4. Okay, if you look at it, the sizes were already shown on the figure. Yeah, you can see 12 inch, 12 inch, 12 inch, 12 inch, 8 inch. Okay, so we already assumed the discharge in each pipe and then the total flow entering, and based on that we select the pipe size. Okay, and when we select the pipe size, we now compute K for each pipe. Okay, we compute K. You can see that, which is the the resistance coefficient. Okay, using either the Hazen-Williams formula or the Das-Weisbach formula. Okay, so we compute K for each pipe and solve for flows in each pipe through the iterative procedure. Okay, which we did in the previous example. So once we do that, we should confirm that each pipe carries the quantities required for that segment and recheck the velocities in each pipe. Okay, you recheck the velocities in each pipe. How? You have the flow rate in the pipe. Okay, when you have the flow rate, you also have the pipe size, so you can find the velocity using what? Q equal AV. Okay, you have the flow rate, you have the pipe size, you can find the velocity in each pipe. Okay, and the velocity, as we mentioned, it has to be within 2 to 5 feet per second. Okay, 2 to 5 feet per second. So this is very important. If it is less than this, okay, then you can change the pipe size. Okay, you can change the pipe size in order to ensure that the velocity is within the range. Okay, because that is very important. And then from there, once the velocity is fine, you can calculate the pressures at the knots. Okay, and compare the calculated pressures to the desired standard pressures. Okay, so once you find the head loss, you can find the pressure heads. Okay, and then you compare it to the desired standard pressures. Okay, at the particular area. All this pressure is given in form of head. You can convert it to pressure. Okay, because the pressure head is simply P over gamma, isn't it? Okay, P over gamma. Okay, the piezometric pressure plus Z. Okay, so you can convert it to piezometric pressure, okay, which is P plus gamma Z. Okay, and then where velocities are more than 5 feet per second, or pressures are low, increase the pipe size. Okay, and repeat the procedure until satisfactory solution is obtained. Okay, in this example, adjustment of the pipe is not required. Okay, so when the velocity is higher or the pressure is low, okay, so you need to increase the pipe size and repeat the procedure until the pressure is satisfied and the velocity is satisfied. And also you should perform the above analysis with fire flows assigned to other nodes and select the final design. Okay. Okay. Okay, and select the final design. So estimates of design flows for the example. Okay, the estimates of the design flow in the pipes, we use, that is, how did we get like the design flow for link AB? Okay, We assume area or population served 5 acres, and the maximum daily unit consumption 4,500 gallon per acre per day. And when you multiply, you get this to get, in cubic feet per second. And the same thing for AC. If AC is to serve industrial area, BC to serve commercial areas, BD residential area, single family, and DE residential area, single family, and CE residential area, multifamily. Okay. So this is how we distributed the flows, okay? And this is the fire demand, which when you add everything up, you have 4.37, which is the total inflow into the distribution network. The design of water distribution network is summarized here, but to gain an actual experience on this, probably you may need to take, like I always tell you, that this course is like a compressed form of about 4 different courses all in one. Okay, so this is like just an idea. We did the analysis, but to do the actual design of a water distribution network where you will do it from the beginning till the end, maybe that should be carried out in an advanced course, a senior elective, like an elective having to do with the conveyance network and distribution system. So in that case, you will be taught how to use the EPANET, how to analyze using the computer program, and how to carry out a design of a water distribution network from the beginning, okay, till the end. That is using the topographic map, assigning, finding the pipe sizes, carrying out the analysis, checking the velocities and pressure heads, and adjusting where necessary, and then coming up with the design flows of each pipe and the other, and sizing the other components of the water distribution network, like pumps, like tanks, like valves, and all the other appurtenances. Okay, but with this, at least you'll have a very good and fair idea of what it entails, to design a pipe network or a water distribution network. And this brings us to the end of the course. Okay. I intend to redesign the course against next term, okay? Because one thing I realized is that there are many sections which were taught in fluid mechanics. I will eliminate or minimize those sections and try to incorporate more sections, in other areas that were not taught deeply, like in groundwater hydrology, we will go deep into it. Like in surface hydrology, we will go deep into it, and probably we may include urban drainage. Okay, so this is my intention, for improving the course delivery. So any question before we start our quiz? I currently have 12 participants only, so one person is still missing. So in the absence of any question, before we begin the quiz, okay, I would like to make some points on our, today we are going to hold our final lab. Okay, there are some simple questions which I normally ask. Okay, in the previous labs, I'm not saying they are going to come out, but I just realized that most of you didn't get it. Most of the time I ask you, what is the conversion factor that you used, when finding CD? Okay, let me when finding CD, the coefficient of discharge. The coefficient of discharge is given usually, we take a ratio of QA to QT. Okay, usually QA, we take it in liters per minute in the lab, isn't it? The actual flow rate. The theoretical flow rate, maybe when we convert, because we'll calculate it using formula, you realize maybe it will come down to meter cube per second. Okay, it will come down to meter cube per second. Okay, so and you need to ensure that, I mean, your theoretical flow rate is the unit in calculating the theoretical flow rate, depending on the parameters, is consistent, because you may have millimeter, centimeter, and sometimes even meter. So you have to ensure the homogeneity of the units, okay, in the formula for calculating the theoretical flow rate, because this has affected some of your results for some of you. Okay, now, when you have liter per minute divided by meter cube per second, definitely you must use a conversion factor. Either you convert meter cube per second to liters per minute, or you convert liters per minute to meter cube per second. But the simplest way is to convert to SI unit, liters per minute to meter cube per second. And how do you do that? Okay, how do you convert liters per minute to meter per second? 1 liter is 1 meter cubed. 1 meter cubed over 1000 liters times 1 minute, convert it to second, is what? Over 60 seconds. So you can see liter will cancel liter, minute will cancel minute, and at the end you are left with meter cube per second. And what is the conversion factor? You have 1 divided by 60 times 1000. You can see 1 over. So this is the conversion factor to convert, so that this will now become meter cube per second. No need to convert anything here if it is in meter cube per second. Okay, then you have meter per second divided by meter per second, and then your CD will turn out to be correct in that case. But if you have any problem with the conversion, then definitely that will affect your result. It will affect the value of the coefficient of discharge that you obtained. Okay, coefficient of discharge, the value is usually for most of the structures, let's say 0.6 to, let's say 0.9, or sometimes up to 1. But you have seen in some of your results, some of you are getting the coefficient of discharge 0.01. Definitely, you know this is wrong. Some of you are even getting minus. Some of you are getting 0. maybe 3. This is too small. This is too small. And for the height of the channel, I told you clearly, do not use a ruler to measure the height of the channel. Use the depth gauge. When you use the depth gauge, it will give you 95. When you use a ruler, it will give you 120. And when you use 120, it will affect your result throughout. Okay? You use the depth gauge because you will be subtracting. Depth gauge gives you 95, and then when there is flow, you use the depth gauge to measure this. And when you subtract, it gives you the depth of the water flowing. Okay? And that is the correct thing to use, not 120. When you use 120, if you check, I will cycle that 120 because it will affect your result all along. Okay? So here, someone wrote 1000 times 60. No, it has to be 1 over 60 times 1000. You have to divide the actual flow rate by 60 over 1000 to convert it to liters per, to convert it to meter cube per second. And this is very, very important, because that will determine whether the value of the coefficient of discharge is right or wrong, because all the subsequent like discussion is based on the coefficient of discharge. And then, like, one question I normally ask you is, okay, let's say you got the coefficient of discharge to be 0.8. Discuss, comment on the value. Simple comment on the value, because the coefficient of discharge like is actual flow rate over the theoretical flow rate. So it's more or less like an efficiency of the hydraulic structure. Because the closer it is to 1, the better. You remember when we were discussing the mouthpiece, we said it makes the contraction coefficient it makes it 1. It increases the contraction coefficient, and that makes it better. the better the coefficient of discharge, coefficient of velocity, coefficient of contraction, the closer it is to 1, the better. Because that means that the hydraulic structure, it is very efficient in measuring the flow rate or the velocity or whatever parameter you are discussing. It makes it very efficient. But the farther away it is from 1, it means there are many losses, because here the theoretical formula you derive, it means the actual flow rate is smaller than the theoretical flow rate, and it will be smaller than the theoretical flow rate because of losses. Losses are, the factors that contribute towards making the actual flow rate to be different from the theoretical flow rate. So the higher the value of the coefficient of discharge, the better we can see that the hydraulic structure is more efficient at measuring the flow rate if it has higher coefficient of discharge. Is it clear? So this is like one of the comments that I want you to like explain when I ask you, like, comment on the value of the coefficient of discharge. So try to relate. You can simply tell me, like, the coefficient of discharge, it is like an indirect measure of the efficiency of the hydraulic structure. So the closer it is to 1, the better. Okay, so you might get 60, 0.6, you might get 0.7, 0.8, or even close to 1, sometimes even 1. So this is, once you explain it in this regard, then it means you understood exactly what is this value that we are getting. Okay, and again, now with this value, with the coefficient of discharge, anytime we want to use the hydraulic structure, we just need to, because the theoretical flow rate will be usually proportional to the head over the weir or over whatever it is. We just need to measure the head and then plug it into the formula of the flow rate to using the coefficient of discharge to get our actual discharge. Okay, this is one of the application of the coefficient of discharge. When we get the coefficient of discharge, all we need to do when we want to measure the actual flow rate, we only need to measure the head, depending on whether you are, like, if you are using a weir, rectangular sharp crested, where Q is 2/3 CD L root 2G h to the power of 2/3, isn't it? So all we need to do is to measure the head above the crest and then use the coefficient of discharge to get the actual flow rate. This is another importance of finding the coefficient of discharge. So these are the comments that I want you to make when I ask you, comment on the value of the CD obtained. Is it clear? I can see all of you are present now, so I hope you are understanding all this. Let me clear, and then what else? What comment do I want to make again? Okay, then on precautions, you should be very clear on precautions. In all the procedures, I indirectly state all the precautions. Like, for instance, can I change meter cube per second? Yeah, you may decide to change meter cube per second to liters per minute. The most important thing is that the unit has to be the same. Yeah, you can keep liters per minute and change meter cube per second. Okay, if you want to change meter cube per second to liters per minute, how are you going to liters per minute? Then it needs to be the reverse now. It has to be now times 60 times 1000. And that will now change it to liters per minute. Okay, when changing liters per minute to meter cube per second, you divide by 60 times 1000. And when changing to liters per minute from meter cube per second, you multiply by 60 times 10 to the power of 3. Okay, so now on precautions, like I was saying, you need to be very clear and specific. You cannot say, no, measure the height correctly. How do you measure it correctly? If you tell me avoid error due to parallax, parallax is the error that is, you need to read at eye level. When you move up and you are reading below point, then there will be error due to parallax error. You need to read at eye level. So you can say measurements were conducted, readings were taken at eye level. That is clear, very clear to me. Okay, the outlet cover has to be open widely enough to ensure the outflow is not obstructed or is not stopped. That is clear. The flow turbulence, the damping, the mesh that is damping the flow turbulence at the inlet has to be in place to avoid turbulence. That is clear. But some of you are saying fan has to be stopped. Which fan? There is no fan in the lab. Some of you were saying that the ruler has to stop moving before you take the reading. Which ruler is moving? There is no moving ruler. There is no moving ruler. Some of you were saying that readings must be taken by 2 students and then the average found. That is not really a clear precaution per se. You have far stronger precautions than those ones. Okay, you have far stronger precautions than those ones. So all this, when you read the procedure very well, all the precautions are stated there very clearly, very clearly. Okay, yeah, including air. Yeah, can I talk including air? So that depends on, like for instance, when you're talking about the rectangular wear, yes, you need to ensure that the nap is flowing, there is free flow. Okay, it has to be vented. So it depends. There are some precautions that are peculiar to some experiments. Like for instance, when we are using the broad crested weir, you have to ensure, like when you have the round nose, okay, that the round nose has to be upstream. Okay, it has to be upstream. It has to face upstream. And of course, some of you are also like, you have to take average of the flow rate because it fluctuates like 4 different values or 3 different values. Yes, that is important. And you have to either increase the flow rate gradually or decrease it gradually. So all these are precautions that you need to express them clearly. Okay. And then what other mistake do you normally make? What other? And I have all your graded scripts. Okay, I think what will happen, I will bring them to the lab. I will bring them to the lab and give you, all the graded homework, quizzes, and lab reports. I will, if you want to come before and collect them before the lab, you can do that. Otherwise, I will bring them to the lab. And again, group 1 will start at 2, group 2 at 2:45. Group 1 will start at 2 p.m. and group 2 at 2:45 p.m. So they should be there at 2, they should be in the lab at 2:45 p.m. group 2. Okay, and group 1 at exactly 2 p.m. Okay. Yeah, I will give you, per group, you study it, go and conduct the experiment, take the values, then you now separate and, report everything separately. But unit conversion is very important. Unit conversion is very important. Okay. Yeah, there is formula and the formula will be given. Any formula you need will be provided, don't worry. Yeah, any formula you need will be provided. So I think I have said enough. Yeah, I think I have said enough. So now let me administer the quiz. I will post it on the blackboard, and then once you finish, just uh, take a clean copy of the solution and write your ID on top. Write your ID on top of the paper and send it to my WhatsApp number. Okay? And the quiz is just 15 minutes. Okay? It's just 15 minutes. Yes, I have uploaded, so you can start now. Good luck.